All right, so today we have just one problem, one page to work on since we did 3 pages last time. And I'm sort of regretting this now because the first time around, it only took 10 minutes. So our recitation is probably gonna only be 10 minutes, which is ridiculously short, but I don't know. If you guys prefer it that way, uh, maybe. I don't know. Okay, so, but yeah, this last page, all we are doing is we're running through this process of optimization or of finding the absolute min and max values when we're given a closed interval on a specific function. So the process to do that is you find your critical points for your function, and then you plug in to your original function at the endpoints and at the critical points. And the process for finding the critical points is you take the derivative, set equal to 0, and solve. So that's exactly what we have to do for 10. So we're just going to go and do that. So take the derivative, set equal to 0, and solve. This is going to be 6x squared plus 6x minus 72. We set equal to 0, and we go ahead and solve. So for this, we can divide by 6 everywhere, and that's going to simplify our polynomial. 12, and then this guy factorizes rather nicely. X plus 4, x minus 3 equals 0, which tells us that x is equal to -4 or to 3. Okay, but then we look over at the interval that we're trying to find the absolute min and max values for, and that actually allows us to get rid of one of these critical points. So we no longer consider the -4. And so all we have to plug into are, I'm going to list them in order, h of 0, h of 3, and h of 5. So we found all the values that we need to test on. We just then test them by plugging into our original function. And in this case, I use the calculator for this because 72 is a pretty terrible number to multiply against. But I'm going to get 300, negative 132, and negative 32. And so, well, then you just look, what is the maximum value you attain? That's this 3 here. So this is then the absolute max. And what's the minimum value that you obtain? Well, that's this guy, negative 132. So this is the absolute min value. And if you wanted to, you could rephrase this in terms of a coordinate pair. So you could call this you could say that the absolute max occurs at 0, 3. The absolute min occurs at 3, negative 132. You could totally do that if you wanted to. Okay. Any questions so far? No? Okay. All right. Well, then the last problem for today is 11. And really, like, it's split into 5 parts, but you should really think of it as just one problem. It's really just one problem. And for whatever reason, he decided to split this into many, many different parts just to kind of step you through the process, I guess. But if you look at like exams, you're not going to see this as phrase that's 5 parts. You're going to see this phrase as just one problem involving optimization. So the setup for this is like given some fencing, and you want to optimize the area, which in this case is going to be maximizing the area. You want to maximize the area of the rectangular thing that you're trying to make. And so we're going to use x and y to note the sides of this rectangle. And A is just saying, okay, set up an equation of the perimeter, basically. So because you're given 20 feet of fencing, you should use all 20 feet. So that's just going to be 2x plus 2y. B, well, area of a rectangle is just x times y. And C is kind of where the core thing happens. So in Calc 1, you only learn about optimizing functions of one variable. And if you stare at this guy, in this problem, you're trying to optimize this area formula. You can think of this as a formula of 2 variables. And well, the thing is that the techniques that we teach you in Calc 1 only deal with functions of one variable. If you want higher, if you want to work with higher dimensions or more variables, you have to move on to Calc 3. That's where you learn about how to deal with things in the two-dimensional setting, or in general, I believe the n-dimensional setting will be something maybe you get taught. But here, Calc 1, only deal with functions of one variable for optimization. And so what we need to do is actually rephrase this as a function of one variable. And the key thing that lets this happen is actually this part A. Part A gives us a relationship between x and y, which we will discover now. So I'm going to now divide by 2, and then I can just solve for y. And the reason to solve for y is because we want to actually get rid of the y, so we want to rewrite y in terms of x. Okay, so this is going to give us that y is equal to 10 minus x. Great. Now we can take that and replace out the y here. So we get a is equal to x times 10 minus x. And I left this extra space here because I want you to think of this now as a function of x. A is now a function of x. Okay, that's great because now we can run through this optimization process that was part of this part 10, basically, as well as, I guess, part 9 as well. So now we're optimizing a function of one variable, and we actually have a closed interval. Now, the problem just gives you that closed interval, but normally you actually need to think about it and figure out that that is a reasonable range of input. The way you think about it is by considering this picture. Okay, so, well, it's very straightforward, actually. So this is basically just common sense. Like, what happens when you let x be 0? Well, you don't get a rectangle where you get like a straight line. You get a line segment. You get what in math you might call a degenerate rectangle because you've made one of the side lengths equal to 0. So it's no longer really a rectangle. Okay. And so that is a very natural endpoint for our possible input. And the same thing happens with x equals 10 feet. If you let x equals 10 feet, what you do is you let both of these two be 10 feet. You've used up all 20 feet you're given. Your y is 0. So you've made another degenerate rectangle. You've made the other side equal to 0. So that's why you would naturally come to this interval, which is just given to you out of nowhere. But you're supposed to figure that out normally. Okay. And so now we have a closed interval. That's great because we can then use this closed interval method, right? Set equals 0, solve, plug in at the endpoints, plug in at the critical points. It's a very formulaic process that we are teaching you to get used to. Okay, so that's why, so yeah, go ahead and do the whole finding critical points. We take the derivative. Oh, first I should probably distribute this. 10x minus x squared. There we go. Now I've distributed it. Now derivatives are easy. 10 minus 2x. Right? We set that guy equal to 0 and we solve. When we solve, we're going to get x is equal to 5 feet. Okay. Right. Now, closed interval method says we should plug in at the endpoints as well, but here we have something nice in that because our endpoints were so conveniently chosen, when we plug into this area formula, we're just going to get 0 since the rectangles are degenerate. We immediately know those are 0. Okay. And for 5, well, we look back on this guy and we get 5 times 5, so we get 25. And I may as well put the units feet squared. Okay. So this guy ends up being the absolute max. Right? That's what closed interval method will tell us, which therefore means that this maximizes the function of area, which is precisely what we're looking for. And then part E is just saying, well, what are the actual dimensions? We found the area, go back to the dimensions. How do we construct this guy? So dimensions. So in this case, like we know X, and if this problem was more complicated, we would have to actually plug into like this guy that then gives us Y in terms of X. We'd have to plug into something usually, but this is just 5 times 5. So it's for this problem, it's a little bit simpler than usual, I would say. So 5 feet by 5 feet is the answer to part E. Right, and so that's the end of the problem set. Are there any questions? Well, if not, then I can stop recording.